first of all, I have made two parts before coming here, okay? And the first example is actually about the simply supported beam. So you all know what simply supported beam is, okay? So simply supported beam is actually pinned from one side. It's hinged from one side, hinged. So you have a pin connection on one side, and on the other side you have got a roller connection, okay? That is called a simply supported beam. So this is just a simply supported beam, and I made it using SolidWorks. So let's discuss what the dimensions are actually, so that you know it beforehand. So this is actually 25 millimeter, okay? It's the cross-sectional area. So this is 25 millimeter and this is 100 millimeter. So the dimensions are in millimeter, okay? And then after that, I made extrude boss for this one, okay? So you can see that the extrude boss is 2025. Okay, so I actually made it 2025. The reason is that this side, I want to keep the distance from center to center equals to 2000. Okay, so from here, from the center to the edge, the distance is 12.5. And from this center to the end, the distance is how much? 12.5. So this is actually 25 millimeter more. Okay. And the diameter of this hole is actually, you can go over here to evaluate, measure. You can see that the diameter of the hole is 15, okay? And this one is actually going to be, radius is 12.5, so the diameter is 25, okay? So it's like this. So this is just a simply supported beam, and we want to do the FEA analysis on this one, okay? Now what we are going to do, we are right now in the model state. So you can see at the bottom, okay? So there is motion study as well. You did motion study, 3D views. You can get different views as well from here. And this is model. And in the model, you have this tree, and you always make part in the model. Okay, so I made it beforehand. Okay, before you come, before we start. Okay. Now what we are going to do, we have to apply a distributed load on this one. Okay. So I'm going to apply a distributed load. So I will come first of all over here to simulation. Okay. Let me, this one. Why this is actually coming over here? Pin toolbar, unpin. Okay. Can anyone tell me how to remove this? Because it's coming over there. Okay, fine. So what you have to do, look, it comes again. Can I remove this one? Yeah, here. Okay, this is better. So what we'll do, we are going to come to the tabs and we will come to simulation. If this is unchecked, then you will not be able to, use the simulation. So this tab is not going to be available. So you have to check this one, okay? And you can go over here to add-ins and you have to check on this side as well, okay? So if you are not going to check this, you will not be able to do the SolidWorks simulation, but okay. And if you do not check this one, which is over here, simulation, the tab is not going to come, okay? So the tab is going to go away if you uncheck, but still you can do the simulation. You can do simulation from this one, okay? But if you, for example, uncheck this side, okay, which is actually over here, not over here, in the options, in the add-ins, if you uncheck this side, you will not be able to do simulation at all, okay? Do you want us to save simulation data? Yeah, so you will not be able to do it, okay? So simulation is gone from here. So this thing you need to take care of, okay? So this simulation, where is it? There it is, okay? So this simulation needs to be checked, okay? So that you get the tab over here, okay? And now I'm going to add this tab for simulation over here as well. This is here. So you can do start simulation from here, or you can start simulation by using this tab, okay? Now, what we do, when we come to the simulation, we go to new study, okay? Now you can do different types of simulation like static, frequency. Frequency is related with the vibration. Then topology study, design tree, thermal, something related to, like you apply heat and it's going to expand or something. Buckling, when you apply an axial load, the thin features or the thin sections, they actually buckle. Buckle means they become like circular in shape. Okay, you can do fatigue analysis, non-linear, even you can do linear dynamic loading as well. Okay, this is drop testing. You hit it with something, okay, and then see what is going to be the impact. Then pressure vessel design. These pressure vessels are used a lot. So right now we are going to do the static study. Static means you apply load and it's going to become in the equilibrium. Okay, so it's not something like a dynamic type of analysis. It's a static type of analysis. You apply load, it's going to eventually come to equilibrium or it's going to fail. Okay. So we click OK. This is used 2D simplification, right? By default, this is always in 3D. So if you want it to be in 2D simplification, then you can check this. It's going to make the study easy. Okay. So we click on this. You can write down you can name it anything. For example, I use 01. Okay. So when I use 01, the 01 is going to come over here. Now you will see something which is actually over here. Okay. And you have to start from the top and you have to go all the way down to the bottom. Okay. So this is simply supported beam because the name of the file is simply supported. So what I'll do, I have to define the material first of all. Okay. This is the first thing. So you come over here and you click on apply material. Okay. So you come to this side and you apply material. Now these are actually all the materials available in SolidWorks. Okay. These are materials available in DIN, like European use DIN normally. So this is available in SolidWorks library. This is also available in SolidWorks library. These materials you can define by yourself. For example, the material is not here. The material which you want to use is not here. You can define or you can create a new category. Okay. For example, you can even create a new library. Okay. New category means that there is going to be, you can define a new material under this category. Okay. For example, I say ABS. For example, ABS is not here. So I can define an ABS material. Okay. And click apply or save. Okay. So you can have like tables or data or anything for this one. Okay. So new material. So now you can have new material. So this is actually the category. And now you are going to define new material. For example, the name is again ABS. Okay. So you come to over here and just define the values. So define elastic modulus, Poisson ratio, shear modulus, density, yield strength. Remember, these two things need to be defined. If you are not going to define elastic modulus and Poisson ratio, the SolidWorks analysis cannot be done. The rest is like optional. Okay. Mass density is required when you want to include weight or you are adding centrifugal forces, the effect of centrifugal forces. Then you have to define mass density as well. Okay. Yield strength is something which is optional. If you leave it, the study can be done. But yield still tells you and give you an idea whether the material is going to fail or not. But it has nothing to do with the study. It's not going to give you error. Okay. But these elastic modulus and Poisson ratio, if you do not define them, then there is going to be an error because this is required in doing these calculations. Okay. So these two items are mandatory. So if, for example, the values are not there or you are choosing a new material, the value is not there. So you are going to come to the internet, search it. What is the best value? Or you can get the values from the papers, research papers. Get the value from the research articles and place it over here. Okay. So if a material is not here, you are going to apply from this side. Okay. Right now, I am thinking that I am going to choose something which is actually over here. For example, AISI 1020. AISI stands for American Iron and Steel Institute. Okay. So they actually, give numbers to different types of materials. So different materials have got different configurations. Okay. So I'm defining this one, for example, and you can see that the elastic modulus and Poisson ratio are given. What are the units? Newton meter. So you can come over here. For example, you do not need in Newton meter. You need it in English, IPS. You can change. It's going to be in PSI. Okay. You need in metric. Now metric is actually in kilogram force per centimeter square. Okay, and even you can use in SI, but the unit is, this is very commonly used. Okay, so Newton per millimeter square, megapascal. So Newton per millimeter square is actually equal to megapascals. So the elastic modulus, you will see that is going to be in megapascals. This is very commonly used unit. So you can choose any unit you want. Okay. So category is steel. This failure criteria, you know, there are different types of failure criteria like von Mises, how the material is going to fail. Okay. Von Mises, then there is Tresca. Then for brittle materials, there are different criteria. Okay. So this is actually fixed. You cannot do anything. And you click on apply, the material will be defined. Okay. So when you come over here, so this is ABS right now. Let's see why it's not applied, why it's not coming. So I'm going to come over here, select this. Okay, select this SI, apply and close. So you will see that AISI 1020 is over here. Is that okay? Okay. Now connections are used when I'm going to do the next topic, when I will, because we have got two analysis in this session. Okay, so this is the first one. This has only one beam. The next one has got two components. So in the two, when you have two or more components, then you use connections. Okay, if you do not have more components, if you have only a single component like this one, then there is no need for doing any connection. So what this says, these geometry based interactions, right click connection faultless. Okay, so there is no interaction right now with the another component, so we are not going to do anything with connection at this stage. Now fixture is something where it is fixed. What are actually, you know, it is fixed somehow to the surroundings. For example, you have a pin over here, the pin is inserted inside, and the pin is actually connected to the ground. Okay, on the other side you have another pin, and that is connected to the roller. Okay, so you need, this thing is going to come under the category of fixtures. Connection is something when you have two or more bodies and how they are connected together. Okay, so there is a difference between them. Two or more bodies will further be connected to the ground. That portion will come under the category of fixture. Okay, so you come to the fixture, there is something which is called fixture advisor. Advisor is something which is like a help. Okay, so if you want to see help, you are going to come to this advisor. Okay, otherwise you can go to the SolidWorks website and you can find a lot of help material even on YouTube. Okay, now this means fixed geometry, you fix it. Okay, fixed geometry means you fix it, and it's telling you what it means. So this portion can be fixed. This means it's going to be fixed in X, Y, Z coordinates. Okay, this is what fixed geometry means. Okay, then you have out a roller slider, then we have got a fixed hinge. So it tells you the diagram as well. It gives you a diagram. What is the meaning of hinge? Okay, so hinge means it can rotate. Okay, then you have got a roller slider. It's going to slide like a roller like this one. Okay, so this is fixed one. And then let's see what are the other types. So solar sliders again here, fixed hinge. This is elastic support. You can add some elastic support like a rubber at the bottom or a spring, for example. This is something like a bearing fixture, a fixture with the help of a bearing, foundation bolt. And there is something which is called advanced fixture. This is used a lot. Okay, so I use this advanced fixture a lot, and this was something which is very helpful. Now I see that this is actually a cylindrical surface, and in this cylindrical surface, it's connected with a pin. Okay, so what I'll do, I can, now this symmetry and cyclic symmetry is actually different thing. Okay, maybe if we get time, I'm going to discuss about it, but it's something different. This used reference geometry, this is something like a journal type of reference geometry. And the particular types are on flat surfaces, on cylindrical surfaces, and on spherical surfaces. So you can go to reference geometry and do all the work which are done by these three, or you can quickly go to these options, okay, and apply the constraints. Okay, so instead of going over here, I can straight away go to on cylindrical surface. But remember, I can go over here to reference geometry and do the same thing as well. Okay, This reference geometry can do all these three things except the top two. Okay. So I can go over here to cylindrical surfaces, and I'm going to select this cylindrical surface, which is actually over here. Okay, so let's bring it over here to this side. This is the surface. Okay, so this is phase one, which I have selected. Now, when I come over here, these are three options. Okay, when you make these options activated, this means you have applied the constraints. Okay, and the unit is millimeter. So what this tells you, you can see the diagram above as well. It tells you that there is restriction in the radial direction. Look, it gives you three types of arrows: radial, axial, and circumferential. Okay, so these are three different types of arrows which you can see. So I do not need circumferential. The reason is that I want that this should rotate. Okay, because this is connected with the hinge, and I want that they should rotate. Okay, I do not want to restrict the rotation. So I'm going to, disable this. So when you disabling is something like this. When you disable this, this means it can freely rotate. Okay, but because this is connected with a pin, and pin is of course connected somehow to the ground, so this cannot, go in the axial direction. So what is this? This is for axial one, and I'm saying that the value is 0. When we say value is 0, this means it cannot move. If you say value is 1, this means it can move in the axial direction by 1 millimeter. It can move, okay? But when you say that the value is 0, this means it cannot move at all in the axial direction. Similarly, I'm saying radial direction, okay? And I'm making this number 0. So this means in the radial direction, it cannot move. Radial means along the radius. Okay, so it can only rotate, but it cannot, go anywhere else. And this is what hinge is. So in hinge, only rotation is allowed. No translation is allowed. Okay, this is actually the definition of hinge. So we come over here, and that's it. This is actually color setting. You can change the colors if you want anyway. Okay, so you click OK and done. Okay, so this means now it cannot move in radial direction. It cannot move in axial direction. I'm going to apply the same thing on the other side. Okay, so you can see that it's written over here on cylindrical surface. Okay, you applied fixture. Now I apply another fixture. Okay, go to advanced one. Okay, go to cylindrical surfaces. Select this radial, select this axial, make it 0. Okay, you can see this diagram as well. It's telling you everything. So click on this one. So there is restriction in movement in the radial direction as well as in the axial direction. And what type of restriction? Translation. So you are restricting the translation, the motion. Okay, so it cannot move this way, or it cannot move along the axis as well. You click OK, done. So now you have got two fixtures. Okay, any question? Yes. How many students? 12, 15. Okay. Okay, now what we are going to do next? We have to apply loads. Without applying load, you are not going to get anything, isn't it? Now, there is something which I need to tell you. For example, you can apply load on the entire length of the beam, or you can apply load on a certain, on certain area. You get my point? So if, for example, you want to apply load on a, let's go to this option, and I want to apply, this is again an advisor. Advisor means if you want help, go to this side. You can apply force, you can apply torque, you can apply pressure, you can apply the weight, gravity. Centrifugal is something related with the inertia. Okay, then bearing load, temperature, prescribed displacement. Prescribed displacement means you have said that, okay, this is somehow initially displaced. For example, this side is initially displaced by 5 millimeter, for example. Consider that the displacement is 5 millimeter, And now give me what type of stresses are going to be induced in this beam. Okay, so this is called prescribed displacement. So you define the displacement, you know that somehow, you know by calculation that okay, it is actually displaced by 5 millimeter. Now tell me what is going to be the stresses. That is called prescribed displacement. Okay, so I want to apply force. When I click on apply force, it asks me, it tells me, how do you want to apply force? Normal or selected direction? When I click on selected direction, it gives me 3 options. Okay. Remember, this is all uniform distribution. Now, if you want non-uniform distribution, you have to come over here. Okay. Right now, uniform right now I am applying uniform distribution. So first of all, I have to select the face, and it says over here, face, edge, vertices, reference point for force. So let's say I want to apply force on this side. Okay. And if it is normal, you will see normal. If, for example, you do not need the normal direction, what you can do, you can come over here and click select direction. Select direction means I'm going to select an edge. For example, this edge. Okay. So if I select this edge, the direction of the force is going to be along the edge. Okay. And you can reverse it. Look, this is there. As you select this edge, only the other options are gone. Look, when I delete edge, okay, so where are the options? Okay, well, let me see, do it again. Okay, normal, select, this is the face. Okay, so okay, so select direction. For example, I select this direction, then you will see a long edge. Okay, I can select any other direction as well. For example, I select this direction, okay, so this means it's along the edge. Okay, look at the directions of arrow. Okay, but if I want to have normal, it's going to be perpendicular like this. Okay, so this is normal. So right now I want to apply a normal force. You can reverse direction as well if you want. Okay, this per item I'm going to tell you afterwards. Per item, right now we have got only one item. For example, you have like 1, 2, 3, 4 circles. Okay, you have 4 circles, and you say per item is, for example, 1000. This means every circle is going to have a force of 1000 Newton. Remember, this is not stress, this is total force. Okay. And if, for example, you say want that you have got 4 circles over here, and you want that all the circles should have a total force of 1000, then you will select total. Okay. Right now, because we have got only one option, that's why this is disabled. Okay. So if you want to apply normal force, you can apply like this. But for example, I want to apply force on a certain area. What I am going to do now? Okay, this is important. So what I'll do, I will come over here. I'm going to cross, and I'm going to divide this surface into 2 regions, or 3 regions, or 4 regions, whatever. So in this situation, I'm going to come to the model. I will come to the model. Okay, I'm right now in the model view, and go to features, curves, and split line. This is very helpful, but remember, this option is not available in simulation. This option is available in models. Okay, it's not in simulation. You come over here, you select split line, and then it asks you, okay, where is the sketch? So you need to make a sketch first of all. Okay, there are 3 options: intersection, projection, and the first one. But this projection is very important, very common. Okay, so you project the sketch onto the surface. So for that, you need to come over here to the sketch, select this surface, and make, for example, a sketch over here. Okay, one sketch here, for example, one sketch here, for example. Okay, click OK, and go to features, go to curves, split line. Look, the current sketch is already selected. Now select this face. So this means whatever you have made in the sketch, that will be, like printed on the face. And the face will be divided into 2 circles. Okay. So I click, this is called projection. You are projecting the sketch onto the surface. Now you see what? You see that this is a separate surface and this is a separate surface. Remember, it only divides the surface, but it doesn't divide it into different bodies. It's the same body. You can come to this section and you can see that it's actually the same body. Okay. So you can see that the body is not divided. Only the face is divided. Okay. And this is actually our requirement. If we do not divide the face, we cannot define the forces. Okay. So I'm going to come back to my study, which is 01. When I come to my study and I come to external loads and I apply force, what is the I can select this region and this region. Now look, as I selected the other region, this total is what? This total came in. As I'm going to remove this total is going to go away. So as I'm going to select this total is going to come in. Okay. Now you can say that, okay, 1000 Newton is actually distributed on this and this plus this. Okay. So the total force is 1000. Okay. Or you can say that per item means this is going to have 1000 and this is also going to have 1000. This means per item. Okay. Total means both of them is going to have a total force of 1000. Okay. So I think now you understand what they actually mean. Okay. But I do not want to, apply force on this and this area. I want to apply force on the entire area because I want to relate this thing with your theory as well. Okay. So I will come over here to external load, click on force, select this region. Now we have to select this one separately and select this because it's just a different phase. And what I say, total is how much? 1000. Okay. So this means the whole area has got a force of 1000 Newton. Okay. So the direction, let's see the direction. Direction is okay. Click done. So all the area is going to have 1000 Newton. For do not worry about this. They all have a uniform distributed loading. Okay. Although it seems that this is having like a higher value. It's not like this. Okay. So it's written total. Okay. So total means the whole thing has got a force of 1000. Now what you do, you come to the mesh. Okay. And you click on mesh. And then it says mesh advisor, again the help thing. Okay. Simplify models for meshing. If you need a simple model, you go here. We are going to do create mesh and mesh control. Okay. In this, and we are going to discuss about details and summary as well. Okay. You can do the mesh quality plots as well. Anyway, these are the two main things: create mesh and mesh control. So first, what you do, create mesh. When you come to create mesh, you can set the quality, whether you want to have a coarse or a fine mesh. Let's do the coarse one first of all. Okay. Mesh quality is over here. Mesh quality over here is high. Over here is draft. Draft is, like an inferior type of mesh. Okay. First of all, let's discuss what mesh is, because some of you are new, I think. Maybe you do not know what mesh means. So mesh actually divides this whole volume into small parts, and we do the calculation on small parts, and then we combine the whole result. This is what finite element analysis is. Okay. So you will study this in 489. Okay. So I'm making a coarse mesh right now. And I'm saying issue warning for distorted elements. If you think that the element is too much distorted, like very long or something, then issue warning so that I know that, okay, the distortion is there. Otherwise, you can uncheck this. Click OK. And look, it's making mesh. Now, these are actually called the elements. Okay. It's something like a tetrahedron. What is tetrahedron? Okay, so tetra, HED, Hadron. Okay, so this is called tetrahedron. Okay, so it's a tetrahedron type. It has got one, two, three, four triangular surfaces. How many edges? Six edges. How many faces? Four faces, four vertices. Okay, and six edges. So it's a tetrahedron. Is kind of pyramid. Okay, so this is actually a tetrahedron. So how many nodes? Nodes are actually the corner points. Remember this thing. And each node has got certain degrees of freedom. Degrees of freedom is something which tells you that in how many direction each node can move. Okay, so you have one, two, three nodes, and nodes are something which is actually nodes actually talk to each other. So the nodes of an element talk to the nodes of another element. Okay, remember this thing. This is the theory of finite element. You will study it afterwards. We are not going to go into detail, but you write the equations of the nodes. Okay, and then you'd solve everything. So the edges or the faces, they actually have no meaning in terms of calculation. Nodes are very important. So what are nodes? One, two, three, four. So this has got four nodes, and if each node has got 3 degrees of freedom, for example, translation in X, Y, and Z, this means the total element has how many degrees of freedom? 3 multiplied by 4 is 12. So this element has got 12 degrees of freedom. And remember, there is going to be another element which will be connected with this. So there is going to be, it's a complete chain actually, which you can see from this side. So we have got tetrahedrons, okay? But this one is actually a draft type of tetrahedron. But there is something which is given over here, and it says, if I come to this side, okay, so edit definition, not this one, create mesh. So if I come to this side, this is draft one. Now the high quality has a curved edge. You can see it's curved, and they have got extra nodes in the middle at the center as well. Okay, so this one is going to have 1, 2, 3, 4 plus the nodes in the middle. So 1, 2, 3, 4, 5, 6 extra nodes. So this is going to have 10 extra nodes. Sorry, 6 extra nodes. So total in 10. So this has got 4 nodes. This has got 10 nodes. So this means the calculation for this one is going to be like 2.5 times more as compared to this one. Okay, so this is going to be like something quick, but it's going to be less accurate. You can always make this one to go to draft, or you can make this one go to high quality. Okay, so you can always move it to the draft or high quality. So this is called mesh quality actually. Okay, so mesh parameters. Now this tells you actually what is actually going to be the maximum element size. What is element? This is the minimum element size. And this is the number of elements in a circle, minimum number of elements in a circle. And this is called element size growth ratio, 1.4. But anyway, these two numbers are actually, they tells you a lot of things. Okay. So what is the maximum element size and minimum element size? So what is maximum and minimum? It's actually the length of the element. So if I come over here to show mesh, where is show mesh? Yeah, there it is. So maximum is going to be the maximum length, minimum is going to be the minimum length. Okay, so this is maximum and minimum. So it tells that maximum is something around 14, I think, and minimum is 10. Okay, fine, that's fine. But if you, for example, we want to look at this. This has got 1, 2, 3, 4 elements in the depth direction. But if you want to make a finer mesh, what you do? You come to, you move this over here and click OK. And now you will see that the number of elements has increased. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements. Okay. So the number of elements has increased. So the finer mesh is going to use more computational power as compared to the coarse one. Okay, but coarse ones sometimes are required to get a general idea how it's going to behave, how the part is going to look like, or how it's going to behave. Now after that, Don't do anything with this. This is, I don't know why they have placed it over there. Okay, define edit. I don't know exactly. Stress and strain. This has nothing to do. So come to this side, run study, and you can do the run study from here as well. Create mesh and run. Okay, or you come to this side, run study. So when you run study, now the study is done. Okay, and you see something which is like this. What has happened? Why it's upside down? Okay, isometric. There it is. So this one. Okay. Now you will notice that the deformation looks too high. Why? Because SolidWorks automatically chooses deformation scale by itself. So what it says, the deformation scale is how much? 50 times. So if, for example, it has deformed by 1 millimeter, SolidWorks has, made it 50 times more. This is what it has done. Just to, like, like, like what we say, like give like for more weightage, you can say, okay, that actually this is not the actual deformation. So how we can go and change the deformation? You can come over here. How can we go and get the accurate one? So you can come over here to this side, and there is an option, edit definition, add chart options and settings. You can click on any of these three. They all come in the same box. Okay, so you click on this one, and there is actually something which is called automatic. So look, automatic deformation is how much? 50. You can click on true scale and click OK. So look, this is true scale. This is the true deformation, and you will see that it's very small. This is something true. In actual, it's going to be something like this. So the forces are just nearly touching the surface. So this is actually the true deformation. And you see something in the blue over here. What is the meaning of blue? Can anyone tell me? Blue means very low stresses. But why you have blue in the center and red at the ends? You have red at the
Neutral
end.
axis.
This is neutral axis. Very good. So this is neutral axis. And remember, you have high stresses on the so on the top side, you have what? Compressive stress. And on the bottom side, you have tensile strength. Okay. So this is neutral axis. Okay. So this is von Mises stress. Now, von Mises stress is actually based on distortion energy theory. Okay. So what is the maximum distortion energy? Based on that, you find out a single number which is going to tell you that this is going to fail or not. Okay. That is actually a single number. If your stress exceeds, now this is, remember, for ductile material, it's not for brittle. For brittle, you cannot use von Mises. Okay. You have to use some other, I think, maximum principal stress, something like this. Then another theory. For ductile, you use von Mises or Tresca. Okay. But von Mises is more widely used. It's more accurate. Okay. And it depends on the maximum distortion energy. So now something there is important, and it says that the yield strength is how much? 3.51 into 10 to the power 8. Where I got this number from? I got this number from here. Okay. So you come over here, this is defined 35157. It's the same number, 3516, round it off. Okay. So it's the same number. Okay. 10 to the power 8. Now you see that the maximum stress is 2.4 into 10 to the power 7, which is very low as compared to the yield. So this means there is a very high factor of safety. It's never going to break even. Okay. Under the application of this load, it's never going to break. Okay. And what we can do, if we, for example, want to find out where the maximum and minimum are, go to edit definition. Okay. Go to edit definition, go to chart options and click on show minimum and maximum. Okay. So this minimum and maximum is going to show you where actually the maximum minimum lie. So look, the maximum is over here somewhere on this side. But I think this whole is, almost like maximum. Okay. and the top is also maximum, and minimum is also over here. And you can consider that this has nothing to do with the loadings. Okay, so this is the minimum. Okay, so this is one biases. Now this one is displacement. Okay, this is displacement. And remember, again, deformation scale is 50 by default. Somehow it's choosing 50, but you can change it to 1 as well, the true value. Okay, so this is displacement. It's telling you, okay, how much is the displacement? So the value is 4 millimeters. Now this is URES. It's like a resultant displacement. It's not a displacement in X, Y, or Z, but it's a resultant of all three. So which is actually 4 millimeter over here in the middle. You have the displacement, and it gives you the strain as well. Okay, so you can click on show, and as you click on show, it gives you the values of strain. Okay, E strain. And if, for example, you want something else, for example, a factor of safety plot, you click on this factor of safety, and you get click all or selected bodies. Do you want it for the selected? Now we only have one body, so there is nothing, but you can use this option for selected bodies as well. Okay, but all means all bodies. So we have only one body, so this is not going to, make sense. And you can set the upper limit of sector of safety as well over here. So it's going to give you, like, for example, 3. You can say that, okay, the upper limit is 3. If it is below 3, this means, consider it's fail or something. Also, it's going to give you some notification. I've never used this, but it gives idea what it means. Okay, so we do not want to do this. Let's click on this, and you see that the factor of safety is 14. So at the center, the factor of safety is how much? 14, which is too high. Okay, so this means you can make the material thin. But on the sides, on this side, this blue thing, this has got a factor of safety of how much? 2000. It's something into 10 to the power 5, almost around a million. Okay, 1/5 of a million. Okay, so this side has got a very high factor of safety. But anyway, this is not actually, the area of our interest. The area of our interest is actually the middle portion, where you have a very high factor. And again, you can click on this edit definition, not this one, chart options. Okay, and click show maximum and minimum. Is going to show you maximum and minimum. Okay, so where the maximum lies, where the minimum lies. Okay, so the maximum is actually in the middle. Okay, now there are some more things I want to discuss with you. This is the beam problem. Okay, this is the beam problem, and let's do some calculation for this one. Okay, so I have made a PDF slide. I did not get enough time, that's why it's not made very nicely, but you will, I think, understand it. Okay, so yes, do you have any questions? Someone is raising hand. Any questions? So tell me. Is it clear till here? Okay, now where is it? 303 workshop, this one. Okay, now this is actually, the cross-sectional area, 100 by 25. The distributed load is 1000. The center to center distance, center to center means the distance from this circle, this center point to this center point is 100. Okay, so it's 200, sorry 2000 millimeter, which is 2 meter. Now you know that this I have taken from the RC Hibbeler. So if you have got a distributed loading, okay, you did this one. So you can use this, make a free body diagram, find out the movements, find out the shear forces. So the movements and shear force diagram is going to look something like this. Okay, this is the shear force and movement, and these are what? These are the resultant forces. Let's talk about the resultant force first of all. What do you think? What is going to be the resultant force in this situation on the pins? The total is 1000. The total load is 1000. How much is going to be the resultant on this side and on this side?
500 each.
500 each. Yeah. So you come over here to result and click on list result force. List result force. and click on reaction forces. Now click on this inside circle and click update. What it gives you? 499.91, very close to 500, isn't it? Remember, it's a numerical simulation. So FEA softwares are all numerical softwares. Okay, they solve things numerically. So there is always going to be some error, but this error is nothing. Okay, so it tells you that in the y direction, which is this one, the sum y is how much? 499.91. And in the z direction and in the x direction, it's almost zero. Ignore it. Okay. And this is the entire model. It's telling you all the sum of all reaction forces. The sum of all reaction forces is how much in the y direction? It's 1000. So this is 1000. But if I click on this one as well, okay, and update, so it gives me what? The selection. This is the selection. So I selected two of them. This is the first selection. That's the second selection. 999.84, which is actually in the y direction. These two you can ignore. Okay. You can ignore these two. You can consider that this is because of some error, okay? Computational error. So you can get the resultant force, the reaction force very easily, okay? Okay, second thing is that I got these forces and I want to find out what are actually the bending moments. So what do you think, what is going to be the bending moment? So the maximum movement is actually at this center point. And this is the theory. You can go to this theory, make free body diagram, and you are going to get this formula. But this is how much? WL square by 8. Okay? It's WL square by 8. So remember this number. This is maximum. So we are coming over here to this PPT. Okay? So let's do this one. Insert text. So M max is equal to what? WL to the power 2 divided by 8, isn't it? So is it 8 or 12? I think 8. Yeah. So now this is actually 8. So what is W? W is insert weight per unit length. Remember, it's not weight per unit area. This is how it is defined. So total weight or load, you can say, the load is actually 1000 Newton. How much was the length? 2 meter. Okay. Which is equal to 500. Okay. So you come over here. So it's 500 multiplied by L is what? 2 divided by 8, isn't it? So this is going to be how much? Now this is not going to be 2. This is 2 square. Okay. So this is going to be 4 divided by 8, which is 250 Newton meter. Okay. This is the maximum bending moment. Okay. So yeah, any question, any issue? Where is it? Okay. So this is the maximum bending moment, okay? So which is WL square by 8. Now you come to these formulas. You have done this one. Okay, you can go to the engineering mechanics book. Okay, and you are going to find it out from here. Okay, this is R.C. Hibbeler anyway. So you come to this chapter and it's called bending. So it tells you that this is called, what is this formula? Flexure formula. So you have done this one, the flexure formula, okay? So it tells you what is actually going to be the distribution of stress. So the maximum stress is actually MC over I, where M is the moment, okay? And C is actually the distance from the neutral axis. So you have this neutral axis, C is actually the maximum distance. And I is what? Moment of inertia of cross-sectional area about neutral axis, okay? So this is I. So let's calculate this. So you know I, how do I know I? So insert text box. I is what? 1 by 12, 1 divided by 12, B H to the power 3, isn't it? So 1 by 12 is going to be as it is, multiply by B is how much? In our situation, B is 100 and H is what? 25. Okay. So I'm going to come over here 0.1, which is 100, and H is how much? 0.025 to the power 3. So if I do calculations and everything, I'm going to get 1 divided by 786,0000 meter 4. Meter 4 is the unit, okay? So this is the value of I. So I got this number. So let's place it over here, this one over here. This is the calculation for W. Now what we are going to do next? Find out maximum, okay? So when we click maximum, so what is the formula for maximum? We go to this book. So sigma max equals to MC over I, okay? So sigma max, where is it gone? Insert text box. So S max, S stands for sigma, okay? So it's MC divided by I, okay? So M is how much? 250, isn't it? Multiply by C is going to be how much? 12.5 divided by 1000. It has to be in meters, okay? SI units. What is 12.5? It's the distance from the center to the neutral axis. Why it's 12.5? I know that the neutral axis is over here. So this total is 25. So half of 25 is 12.5. And what is divided by I? So divide by bracket this whole number, okay? This number, Control C, Control V, okay? So when you do this and you put it in the calculator, so you get, I have done the calculation, 2.45 exponential into 10 to the power 7. Okay, this is what you are going to get. It's Pascals, okay? So this is what I got through calculation. So this is the stress which I am going to get either on the top side or on the bottom side. On the top side, I will get compressive stress. On the bottom side, I will get tensile stress. Let's come to this one and see what are actually the forces, okay? So you come over here to stress. What is this stress? Von Mises. Okay, this is von Mises. Okay, you come over here and you define stress plot again. And do not use von Mises. Rather, which one we are going to use to find out those stresses? Which one? Look, these are three components of stress. Normal stress, normal Y stress, normal Z stress. These are three shear components. These are principal stresses. You know what principal stresses are. Those stresses on an element when the shear becomes 0. This is von Mises. This is stress intensity. This is triaxial. And this gives you some error, okay? This is something related to the error. But these ones, the top ones are important, okay? So what type of stress we need? What is this stress? S max. What is going to be this stress? Who is going to tell me? Which one over here? This is X direction, isn't it? This one, first one. Why? Because my stress is actually not in, it's along the X direction. Okay, normal stress in the X direction. It's not shear stress, it's normal stress. You come over here to the theory and you see that what type of stress is this? It's a normal stress. Okay, if this is X-axis, it's the normal stress. Okay, remember, you should know these are normal stresses. Look, it's not shear. This is normal. Okay, this is the neutral axis. So you come over here, you choose normal stress units, you choose this one. And we need to find out the stress at node values. Remember, the nodes actually talk. You can choose the element values as well. Element is going to give you some average number, but node is always preferred. But the problem is that how I am going to find out what the stress value is over here. Okay, I need, this one is going to give me, let's see how it works. I click on this one, and this is X normal, and click edit definition and go to chart properties and show maximum and minimum. So what it is giving me? A minimum value and a maximum value. Let's move it down like this. This is nice, isn't it? Okay. What it tells me now? This top is minimum. It's telling me that it's at the center, isn't it? And this is maximum. How much is the value? Maximum is 2.4. And sorry? Yeah.
I was asking why the minimum is in negative. Shouldn't the
Negative
minimum be at
because
0?
no, this is compressive. Compressives are always negative. 0 is somewhere in the middle. Okay. Look, what is 0? Go back to the theory. This is 0. This is 0. This is maximum. This is like minimum. Okay. Now, in this situation, this is maximum. This is minimum anyway. Okay. This is minimum, but it's maximum in the other direction, the negative direction. Okay. This is maximum in the positive direction. This is 0. 0 is somewhere. 0 is always on the neutral axis. Okay. When something is compressing, you say that it has a negative value. Okay. This is how we define it. Okay. So it says over here as well, negative X. Okay. That is compressive stress since it's X in the negative direction. Okay. So you can see that in the formula, there is a negative sign as well. Okay. So, yeah. Any question? Okay. So we come over here and what we calculated, this is the important thing. We calculated 12.45 into 10 to the power 7, isn't it? But what we are getting over here, 12.4 into 10 to the power 7. So what do you think? Is it a good, is it something good? Yes, it is acceptable. It's a good result. So this means that whatever we found in the theory, we got the same thing over here as well, isn't it? So remember, in numerical simulation, there is always some error. And let's see how much is the error actually. Okay. So this is 2.4. What is the difference? So error is going to be how much? Insert text box error. Error is 0.05 divided by 2.45. You can consider this as a reference. Okay. This can be considered. So it was actually 2.40 in the simulation. Multiply by 100. So if you do this, you get something 0.05. So I'm going to do it on my calculator. Divide by 2.45 multiply by 100. It's 2%
Nearly
error.
2%.
2%, which is nothing. Okay. So if you, for example, increase the mesh, if you make like a higher mesh or use a, like a better elements, this is going to further reduce. Okay. But remember, in FEA, you always are going to get some error. You cannot get, but still 98% accurate result, which is very good. Okay. Okay. So this is done. And then you can do some more things. For example, we discuss about this list result force. You can list result displacement and strains as well. Like you click on this and you can say that, okay, I need stress. Which type of stress? Von Mises. For example, you can choose the normal stress as well. You can choose normal stress as well and list them. And what it is going to do, list all values within 5%. So top 5%, okay, it's going to give you. So when you click on this one, it gives you the list, okay, of top 5% of the element. Look, these all of them have got what values of stress? It starts from 2.4 and it goes all the way down to minus 2.4. One minute. It's giving me, all the elements, I think, isn't it? 2.7. No, it's not giving me all the elements. So you can see it's 2.7 and suddenly it jumps to what? Negative values. You get my point? So it's taking like an absolute, like a mod value. Okay. Top 2% means maximum versus minimum. This is what I think, because there is definitely going to be something in the range of 10 to the power 6, 5, 4, 3. Even there is going to be something in the range of 0 as well, but that is not shown. Okay. But if, for example, I come over here and I say less stress values, which is actually this normal one, but I do not want the top 5%, but let's say I want the 100%. Okay. So if I say, let's say 100%, see what it is going to look. It's taking time. Okay. So it's making the whole list of all the elements. So you are going to get everything, all 100% low. So this list is very big. So it's here 10 to the power 7. It should be 10 to the power 6. Look, 10 to the power 6. Then 10 to the power 5, 4, 3, 2. Look, this is all 10 to the power 6. 10 to the power 4. 10 to the, again, there are a few elements, I think, on 10 to the power 3 range. So you can come over here. Okay. 4. 4, 5, 6. Let's see. This is 4. 10 to the power 3, 10 to the power 2. Look, very few elements in 10 to the power 2 range. Then after that, you just suddenly go to positive side. Okay. So you are going to get all the values. Anyway, 10 to the power 2 is like few hundreds, which is nothing, which is almost 0. Okay. So you can get this thing, and what else? Like this thing I do not want because it's the result equation, something. Factor of safety is important. Stress plot is important. Displacement plot, displacement is something which is related to the displacement, not the strain. So there is a difference between displacement and strain. Displacement is actually in millimeter. Strain is actually a ratio. Okay. So that's it from here. And mesh quality I discussed. I discussed about the loads. Okay, I discussed about the connections, because now how much time is left? 10:38. We have got like few a little bit more time. Let me see if I have covered these things. Okay, one more thing. For example, I want to find out what are the values in this at the center. Okay, I want to find out the values at the center or any location. For example, at 25%. Okay, so what I'll do, I will go back to the model. Sketch a line over here. For example, you can sketch a line. Okay, and give a distance of 500 millimeter. Okay, so go to sketch, smart dimension. This one from here to here is 500, for example, because the total is how much? Total is 2000. Okay, so this is 500 millimeter. And then what I do split line. Okay, so click on this and split it. So now this is splitted. Let's delete this split. Okay, we do not want this anymore. So delete this one. Oh, we cannot, because this is based on that. Otherwise, the my simulation is going to close. Okay, I do not want to do this. Okay, anyway, fine. So this is splitted. Okay, I should have deleted it before, but anyway, don't worry. This is 25%. Let's make it 30%. Let's do this one again and make it 30%. Not 500, 600. Okay, so this is 600, so that we do not disturb this. Okay, so done. So now this is actually one region, this is another region. Okay, so you have one region, second region, third region, and the fourth region. You have got 4 regions on the top. Now come to the model. Okay, look, This is what happened. So I disturbed this one. So now, what should I do now? Actually, what's wrong? Where is it gone? Simulation study. Can anyone have, does anyone have a clue? Okay, there it is. Because there was a red line, I was unable to see. Okay, so rebuilt it. There's no issue actually. What's wrong? External forces. Okay. Create mesh. Oh, there is nothing over here. Well, I think we have to delete it and redo it, this one. Add details, hide, suppress, delete. Okay, let's delete this one and add external loads again. So force, okay, supply load here, not the edge. I somehow selected the edge. This side, this side, this side. Maybe because I have, made another division, that's why it's making trouble. Okay, I made a division. That's why it was making trouble. Okay, so this is total. I'm not going to say per item, it's total actually. So click OK, then go to mesh, create mesh. But remember, the mesh has nothing to do with the loadings. So the mesh was okay. And then click. If you have a yellow, this means there is a trouble. Okay. So you always have to, make sure that the yellow should go away. Okay, look over here, the red is gone. So this is done. Now, what I was saying, I forgot. Yes, I made a split line, isn't it? So I made a split line over here, which is this one. And for example, I want to know list result force. Okay. And I want to know what are actually the forces on this region. Okay. So what I'll do, I will come over here, click on this. Okay. And update. So when I update this, it tells me not the reaction force. No, sorry. This one. Okay. List selected. I want to find out the select stresses. Okay. This result is dumping. This is going to give you the resultant. I want to find out the stresses on this line. Okay. So what I'll do, I will click on this and I will come over here to list selected. When you come to list selected, you are going to enter this line. Okay. You will enter this line. And when you enter this line and update, it's going to give you the values of the stress all the way along this line. Okay. And this is giving you a summary. What is the maximum? What is the minimum? What is the average? What is the root mean square, RMS? What is the sum actually? So how many elements we have? We have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, around 12 and 13. Okay. So you can see that we have got 12 and 13 nodes. These are not elements anyway. These are nodes actually. So when we come over here and click on show mesh, there is an option to show mesh. Show. Okay. This is the mesh. Where is the line? Where was that line? This is the line. Now count the elements. Count the nodes. One. Second one is in the middle. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 nodes. There are 17 nodes in total. And when you come over here and you click on this one, show, and you come to list selected, okay, on selected entities, you come over here. There are how many nodes? 17 nodes. Update, so you will see that there are going to be 17 nodes in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And look, as I'm moving, it's giving me the node 17. So look, as I'm going up, it's telling me where the node is. Can you see? So if you want to know what is the value at a particular, along a particular line, you can do that. And you can make a plot as well. Very good thing. Look at this. This is a plot. How the stresses are actually changing along the length. Okay. So it's a von Mises stress. And look, this is the first node, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, all the way up to 17. Okay. So this is something which is very nice, a nice feature. You can find out the stresses all the way along the length as well. And for example, I want to find out what is the stress over here. Not the stress, for example, this is the normal stress. Let's show this one and click over here, list selected. So if I click on this line plus this line, this is the whole line, okay, and click on update, this is going to give me the stress on this value. Let's plot the graph. So it's giving me something which is like this, okay. So 0 and default. Should not be like this anyway. Okay. 1 minute. This is 2, 6, this, 1.566667. Okay, let's do for the bottom one. Edge this, update. Okay, so at node number on selected entity. So this is the entity actually, okay? And click on update and let's plot the graph. Now it is nice. Now what this tells you, now somehow I don't know what happened because these are, two different lines. Somehow it did not, update it, made it into, a single, as a proper graph. It did not somehow made as a proper graph because of these two different lines. But over here you have got a single line. Now what this tells you, what is this graph? Have you ever seen this graph before?
Maximum moment.
Yes, moment diagram. Look, 2.4 into 10 to the power 7. It's a bending moment diagram, isn't it? And this is what
Yes.
yeah, it's a bending moment. Let me go back again, okay? It's a bending moment diagram, isn't it? It starts from 0, almost 0, okay, and then goes up to 240 in the set at the center, then comes down to 0 again, okay? So along the distance, remember it's a parametric distance, like it's like a normalized distance, okay? So whatever the length is, it normalizes into 1. So it's a bending moment diagram. So goes from 0, this is almost 0, up to 240, and then comes back to the 0 value. Okay, this is 0. So it's a bending moment diagram. And why you have a positive number? Because I have chosen the bottom edge. Okay, I have chosen the bottom edge. The bottom edge is actually stretching. It's in tension. The top edge is actually in compression. If, for example, you make it for the top one, it's going to give you the opposite direction. It's going to give you a negative value. But somehow it's not working because it's divided. Okay, that's why it's not working. Anyway, this is done. So you can do this as well. You can go and click on list selected, and you can do this animation. Remember, this animation is very nice feature. It tells you how, it's actually the stresses are actually changing. Okay, so green and then coming to the red. Now, because this is, this educational product, I cannot change the frame. But in the non-educational product, you can change this frame rate to 10, 12, 15. So in the educational one, they haven't given us that feature. So I tried to do this, but it's not working. Okay. So, but anyway, it gives you an idea. how the stresses are changing. Okay, so this is
Doctor, I have a question.
yes,
Sorry.
yeah, yeah.
Uh, Now you based your analysis only for normal stresses or bending stresses, but what about other types of stresses like shear stress?
Yeah, shear stress you can see as well. Look, for example, I want to see shear stress. So you come over here to the result option, okay? Define stress plot, okay? So this is bending stress, okay? This is the stress, the normal stress which is going to contribute bending. Now in the y direction, you are not going to have any normal stress. Go for that and see, check it, okay? So click on this and click OK. You will get a tab. It's going to give you, look, it's almost same. It's almost like green. Green means what? Zero, nothing. You get my point? So green
Yes.
is over here. Okay, so this means, look, this is actually 10 to the power 3. Remember, 10 to the power 3 is like few thousand. Thousand is very small as compared to, almost it's half of a million. This is half of a million. This is few thousand. So when you have green, this means you have thousand. Remember, there is always going to be some number in finite element analysis. But as compared to million or a half million, thousand is nothing. Thousand is like zero. So this is actually zero. So you see that there is no stress in the y direction almost. Okay, it's a zero stress. So if you want to find out what is the principal stresses or whatever, you can do that and select it. You can find out. For example, there are what bending moment and shear force diagram. So what do you think? Where is going to be what should I select to find out the shear forces? Y direction. I need to find out the shear forces.
It
So
should be on Y. Yes.
on what?
On Y, right?
Yeah, on y direction, but on YZ plane. On YZ plane, shear in y direction on YZ. This is YZ plane. The YZ plane is going to be this in the y direction. So I will select this option, and I'm going to get the shear force. Okay, this is the shear force. So you should know what is actually the meaning of shear force over here in the context of SolidWorks. Okay, so it's actually shear in y direction. This is y direction on the x y z plane. So that's actually a YZ plane. Okay, so you click on this one and you get this shear force YZ plane. Okay, and show. So this is tau x. X means normal. X is actually the it tells you actually the vector of the area. So the area is actually perpendicular to x-axis and the direction is y. Okay. So this
Okay.
is the value. Now, why this value is fixed and constant? Because you know that the shear, what is going to be your shear force diagram, is going to start from 500, it will go all the way to 0, and then it will come back to minus 500, isn't it?
Yes.
So shear force is going to be like this. Let's go back to the R.C. Hibbeler. So you know it from here. So shear force is actually, let's go to this one. This is okay. So it's going to start from WL by 2. L is 2. W is 1,000. No, W is 500, isn't it? So W is 500, L is 2, and divide by 2. So 500 plus 500 and minus 5, which is actually nothing, which is very small value. Okay. So that's why. But you can go and see. Look, as compared to 10 to the power plus 5, this is all green. Okay. But there is one nice feature over here. You come to this side, and you can change the limit as well. It's somewhere in settings, maybe I forgot actually. Normal, thick, scientific. This is scientific, floating, and journal. What type of units you want to see? Number of decimals, how many decimal? Vertical from top, 2%. Horizontal from left. There was something which tells you automatically define maximum value. Okay, stress plot. So at some regions, it's telling us, there are high values of stress. there are high values of stress. Remember, it's not the force. I'm sorry. This is not the force. This is actually the shear stress. And how you calculate shear stress? Come to chapter number 7. There is a formula, there is actually a theory behind it. How you calculate shear stress, chapter number 7, you come over here and you find out their shear stress is actually something found in this way. So you have maximum shear stress at the center side and minimum shear stress at the end side. Okay, let me show you how it is actually. There it is. This is one of the example. Okay, tau equals to VQ over IT. Remember this formula? Tau is what? The shear stress. So in the middle, you have a maximum shear stress. V is actually the shear force, the total shear force, which is 500. Okay, so it starts from 500, goes all the way to 0, and then goes to minus 500. Q is, the area which you find out. Okay, and this is actually, the areas. And I is actually, the second moment of area. T is actually, the thickness, which is B. Okay, and Q depends on actually the area. So where this lies. So it's half h by 4 minus y square. So this is y square, h by 4 into B. I forgot exactly what Q was, but I think yeah, this is the first moment of inertia area or second moment of inertia area with respect to the neutral axis. It's something like this. Okay, so use this one. So you will see that it's a parabola. So at the center you have maximum shear, and at the ends you have like almost zero shear. Okay, this is what you are seeing over here. Look, what you see over here. At the maximum, you have high shear. At the ends, you have like almost zero shear. Isn't it? Yes.
Yes.
Why we have zero over here, everything? This is one important, good, nice question. But when I come to this side, there is all 0, 0, 0. Why? Look
I
at
think
this. This
because
is all
it's more
V.
critical on the edges.
No, look at this formula. Not critical. What do you think? What is going to be the value of V?
The maximum is at reaction points, 500.
Remember, maximum always lies over here at the ends. At the center point, you have almost zero V. What is this? This is V. So you have zero V. When the value of V is zero, what is going to be the value of tau? It's going to be almost zero, isn't it?
Yes.
Because this V becomes zero at the center. Okay.
Okay,
So,
see.
so at the center of the beam, over here, the value of V is zero. But as you move to the ends, the value of V is high. That's why you see red. So try to think, or like join the theory with the experiment or the simulation which you have done. Okay. Otherwise, many people, they like do the analysis, but they do not know what is happening. Is it right result or wrong result? So remember, in FEA, garbage in, garbage out. So if you do not know what is happening, so it's like you are sending in the garbage and you are getting out garbage. Okay. So you should always compare your result with the theory as well. Okay. So this is what I did done. This one is done. There are so many things, I wanted to tell you. It's going to take too much time. But right now, what is the time? 11 o'clock. So there are so many things we can discuss. We can spend a lot of time on each thing. There is one more thing. For example, I want to, okay, that mesh I'm going to discuss in the other parts. Okay. So I think we should stop over here. Okay. Now we will go to the next one. Yeah.
Can you take a cross section when the study is done, so you can see
Course section.
the yes.
Course. Yeah. So this is what I've done. I have used fine mesh. You want to convert it into coarse mesh?
No, the cross section of the part. So you cut the part and you see the stresses inside.
Yes, you can do that as well. Yeah. You can do the cross section of the part as well. Define a plane. And with respect to the plane, first of all, define a plane where you want to do this. Okay. And after that, find out what is actually the stresses on the cross section. You can do that as well. So let's do this one. You click on plane, define the first reference. For example, this is my reference. This center, it's already there. Why it's not showing me? Okay, there it is. Okay. And the second reference is like, let's say this one, and it's perpendicular. I'm saying it's perpendicular. Okay. So no, not this one. I mean, I need some distance. What should I do? Okay, so delete this one. Delete this. I want, for example, on this side. There was a line over here, isn't it? I made a line. Okay. So I'm going to take this as first reference. Okay, edge. And the second reference is going to be this plane, for example, and make it perpendicular. Okay. So I defined a plane. So this is my plane. Now I want to, this plane is already over there. Okay. I want to find out what are actually the stresses on the plane. So you come over here, click on show, and ISO clipping. It's called section clipping or ISO clipping. I forgot actually. So do not select front plane, rather select this plane. Okay. So you click on this plane and click OK, and it's going to show you what are actually the stresses over here. So if you want to see inside, it can show you. Is it fine? And you can find out the values as well. For example, you come over here and you click on probe. This is very important. Probe. Probe is something like an instrument. Okay. You click on probe. You click on this and see what's the value. Click on this. These are all nodes. Remember, the elements are actually made up of nodes. So get the values. You can get as many values you want. So you can go all the way up as well, up, okay, along the line, and get the values of stresses. Okay, these are nodes. Okay, so let's delete this one, for example, and delete this one. So you can delete anything you want from here. Okay, delete it. You can delete anything from here, or clear selection is going to clear everything. Okay, like this. So it's giving you a distribution. Look, you can see that. What is this? It's neutral axis, isn't it? It's a neutral axis. Okay, so shall we move to the other part? Any question? Yes. So just, use these ones, use probes. And there are so many things, to mesh selection. And this is also an important thing. Section clipping. Okay, ISO clipping. This one, ISO clipping. Now, ISO clipping is something which is, going to give you, okay, look at this line, this pointer. It's telling you that, okay, what are actually the region with this much and above value of stress, normal stress. So this is the region with which has got this value or above this. What are the region which has this one and above? This is the region. You can, like invert it as well, flip it as well. Flip means what are the values which are this one and below. Okay, so this is the region, but normally above is actually required. That is more helpful. So you can just move this pointer and see what are the values of stresses which are above and above this pointer value. So this is called ISO clipping. Then we have, section clipping. Section clipping is same thing. Okay, you can do this sectioning and see what are the values of stresses. So you will see, okay, how it's moving actually. So you will see that there is actually a neutral stress. Okay, this is section clipping. You can change the direction of plane as well. This is planar. You can have a circular type of section clipping, a spherical type of, say, like a ball. Okay, so you can like rotate this ball, I think. Okay, I don't know if it's gonna work. Maybe it's for circular faces it works, but for these types of geometries, the plane is going to be a better option. Okay. Any other question? Yes. So we discussed many different options. Now we are going to discuss about connections. Okay. This connection is something which we haven't discussed till yet. So I'm going to save this study, close this. And these are my previous studies. Remember that you can have study number 1, study number 2, study number 3. And if you, for example, want to have another study, what you do? Select this, copy study, name this study 002, 002, okay? And click OK. What is the advantage? Everything will be copied to 002. But your previous one is going to remain saved. Okay, so you can use it later. For example, you did something in 002 and then you find out that, oh no, 002 was not good, 001 was better. So this means you have the previous record. Okay, the previous record is not destroyed. So this is one of the advantage. Okay, so save all, cross this. Okay, now we are going to come to the last option, which is actually over here. Okay, let's close this book as well. Okay, there it is. This one, we need it. And paddle flywheel. Okay, what I did before I came, before I started the lesson, I made this paddle. Okay, this is like a paddle and it has got a key. Okay, and it's a single part. It's a single part. Okay, this is like a paddle. This is like a, you can say a link, and it has got a key over here. Then what I did, I made a wheel, which is over here. Okay, this is a wheel, and it has got a key seat. Okay, this is a wheel. So then I made assembly. Okay, this is assembly, and in the assembly you have got the paddle is inserted inside the wheel. Okay, and I have applied mates. You can see all the mates over here. So if I go to the part, you can see all the mates. So coincident mate, and then I made a concentric mate. Okay, so I made 3 mates. These are the 2 parts. Okay, now we want to do the analysis of this one. Assume that this is, this paddle is connected to, for example, assume that this is actually the paddle of a gym machine, and this is actually the wheel which actually rotates, and this is connected somehow to the belt. Okay, you can consider that, and assume that it's locked somehow. It is, the belt is actually locked, and now it's not rotating. Okay, so I want to do the study on this one. So what I'll do, I will again go to simulation, new study, again go to static. Okay, and then this is my part. Now I have got 2 parts. One is paddle, one is wheel. The materials are not defined. So what I'm going to do first, I will define the material first of all. Let's say the first material is what is this? Which material I have selected right now? What paddle? Okay. Let's say the paddle is actually made up of steel. Okay. It's A2010 steel. You apply it, you close it. So I have defined this material, and the wheel is actually made up of, let's say, aluminum. I mean, wheel should be steel. I made it opposite. Anyway, it doesn't matter. Okay. So let's say it's an aluminum. Let's use, like different. Okay. So it's pascals. Okay. This should be Pascal. Apply and close. It's an alloy. This one is again pascals. Okay. Apply, close. Now, when we come to interactions, connection, look, it has already made a connection. What is the connection? It says global interaction. It's interacting globally, but it's bonded, meshed independently. Bonded means it's glued, welded together. Okay. It is like a permanent type of connection, very strong connection. You cannot break it. Okay. Meshed independently means this is going to be meshed separately and this is going to be meshed separately. This means the triangles which we see are not going to be like this, that you have a triangle which is covering the both areas. It's not going to be like this. Okay. So the triangles for this one is going to be separate. The triangles of this one is going to be separate, but the nodes are going to connect each other. The nodes are going to talk to each other, okay? Then we could go to fixtures. Let's fix, this geometry, fix it from this side. When you fix it from this side, fixed geometry, it's not going to, rotate at all. It's like completely fixed. Remember, it has nothing to do with the fix. Okay. What I've done. Fixture, geometry, fix this, click OK. It has nothing to do with this F. Remember, whenever you come to static simulation, these mates, they are actually, they don't work, okay? So it doesn't mean that these mates are going to make it fixed, okay? These mates are gone. You can assume that they are gone, okay? And this fix is also gone. So when you come to this analysis, this study, so although it looks that it's fixed, but actually when it's going to do the simulation, they have no effect on the simulation. These mates and these fix have no effect on the simulation, okay? So I fixed this. Now let's apply the external load. So I'm trying to apply the forces over here on the pedal. Now it has automatically selected this edge. I do not want to select edge. I want to apply force normal. But when I apply force normal, it's giving something like this. So all the forces are actually normal to the surface. It's going to produce zero effect, isn't it? When the force is like this, it's going to compress the cylinder and not going to rotate it, isn't it? So this one is not going to work. Select direction. We have got one item over here. Now, what direction I want to use? I have three options. Either use this one. Okay. Okay, click on this. Now, I want the force to be in this direction. Now, it's asking me to choose direction. This is the surface, and it's asking me which direction you want to choose. So I will say that, okay, direction along this edge. You get my point? You can choose this one as well. So when you select this one, look, all the three other options are gone. Only this option is available. So you can reverse the direction. You can reverse it. Okay. And let's say that this is 1000. It's 1000. Okay. And that's it. You can have non-uniform distribution as well, which you will, if you want. For example, if you want to have a non-uniform distribution, then normally they do have non-uniform distribution. When you're applying force on a pedal, on this side you have like more force, on the other surface you have almost like zero force. Over here we are saying that everyone is over here. We are saying that this side is having, it's like pushing, and this side is pulling, which is actually practically not the case. But let's, for simplicity, we say that, okay, this side is being pushed, this side is being pulled, and the force is actually acting in this direction. Okay. Click OK. Remember, you can also split it. For example, you want to have the force only on a certain area. You can always, split it. Okay. So split it. Okay. Like you did before. So either you go to the model and then make a split, or you can go over here and do the split. Now what I'll do, I will go to the mesh and create mesh. Okay. So we create mesh. I'm okay with this. This is blended curvature mesh. These are the types of meshes which are available in SolidWorks. This is a standard mesh, the like the least expensive one, or least computationally expensive one. This is curvature based mesh. It has got curvature, and this is blended curvature based mesh, the superior quality mesh. Okay. And mesh quality, we discuss about this. So if you want to have both of them, for example, go down, you can bring both of them down, both of them up, or you can bring one down and one up. It's up to you. Okay. For example, you want to have draft mesh with pedal and fine mesh with wheel, you can do that as well. Okay. But right now I want that both of them should have like a high quality, because I have no problem with the computation. Click OK. And look, it's going to convert this into elements. It's meshed it. Now, what is the type of interaction? between this key and this this thing? These are two components. There is we only have an interaction over here. And what type of interaction it is? Bonded, meshed independently. Now see what is the meaning of meshed independently. Look, this is a separate mesh, separate mesh. This is a separate meshed. And look, the nodes are talking to each other. They are aligned. Can you see? All the nodes are aligned. These are the corners. The corners are actually talking. You will never find that a node is actually somewhere in the center, okay? They all are talking to each other. And you will never find a triangle like this that half of it is over here, half of it is on the other side. Now, go and run a study. So when you run a study, this is the study. What it gives you the von Mises stress. So you can see that where is the maximum one. Come over here to edit definition. Look at the deformation scale, 498. It's too much. This means it's never deformed up to this extent. Okay? This is, like exaggerated. This is exaggerated, okay? It's never deformed 500 times. So deformation is very, very, very small, okay? But we want to see what is actually, the maximum and minimum. Where is maximum? Maximum is somewhere over here, okay? And minimum is somewhere on this side. 1.4 something to the power. So this over here, you are going to have a red. Okay, so
Mister,
yeah, there
can
it
you
is.
show the interaction force between these two parts?
Interaction force is bonded. It's like
Yeah,
glued.
but can you show the force that one part apply on the other?
The force that one part apply on the other.
Yes.
Okay, yeah, this is a good question. List result force. Let's result this. Let's see. List result force. Reaction force. Let's see if we can. Hmm. Select other. This one or this one. So let's select this one. Okay. And update. Yeah, these are the forces. So you come to free body, and this is the force in the x direction, y direction, z direction. This is the resultant force. So this body is actually applying this force. But I'm not sure, you need to calculate it, okay? Why not movements actually, Why movements are not coming? We need to check it actually. And but we can find it out. If, for example, this was how much force? 1,000. So out of 1,000, we are saying that this force is actually in the negative x direction, isn't it? So negative x means, so the force which is actually acting on this side is, it's saying 273. Okay, this is 273. Look, it's there. Minus 4.79 and 5.75. And it's saying that actually the reaction force is actually, this. Okay, so it's over here. I don't understand the meaning of this one. What actually this number means. Because it has to be, if it is in equilibrium, it has to be, it has to be 1000 somehow. Okay. Because you are applying 1000 Newton force, and you should get, on the other side 1000 Newton. But and there should be some movements as well, because you are applying force, you should have a counter movement. So this is not, a better option. We will have to figure it out. I'm not sure about it. Okay, so I will try to find it out. So next time, okay? Or if you are in the class, I will tell you. I will try to find out this. How to find out the resultant forces on the body only. Let me see if we can get something from here. Compare result, create body from deformed shape. Okay, collapse 3 items. This is one thing which we can actually do. Explode view, explode. Collapse. I will have to check it. I have no clue right now. Okay. So, but somehow definitely it should show you what are the forces and moments. It should show you. Okay, but one thing is very important, that where is the maximum value? Where do you think, where is the maximum value? Somewhere over here, isn't it? And it makes sense, isn't it? Because the paddle is actually applying force in this direction, and this is the region which is getting maximum stress. Why? What should we do to remove this stress? Why we have maximum stress over here? Can anyone tell me?
Because of torsion. Torsion.
Because of torsion is actually there, but there is some very interesting point.
Concentration.
Stress concentration. Remember, never make sharp cuts. In SolidWorks, we do say that, okay, this is sharp cuts. Always make fillets and rounds. Rounds are very important. Okay, whenever you have these sharp cuts, you are always going to have high stress values. Okay, so how to avoid this? Make a fillet. Okay, making a fillet is going to remove stress from here. So you will get the maximum value, maybe 10 to the power 6, something 10 to the power 6. Right now you are getting the maximum value equal to 10 to the power 7, which is a very high number. Remember, there is no yield. Why? Why there is no yield shown over here? The reason is that we have two different materials, and both the material has got a different value of yield, isn't it? So that's why it's not given over here. So you have to go over there and compare. Okay, what is this value? What is the maximum value? And compare with the yield values. Okay, but the main thing is that over here you see that the stress values are very small, isn't it? Over here, the stress values are very small, and you can come to this side, which is actually iso clipping and section clipping. You can go to section clipping. Okay, not front plane. I want to choose another plane, which is the right top plane, and I want to see what is actually happening inside. So look, there are no stresses. Why? Almost no stresses, isn't it? Let's see the keyway. Let's see this keyway. When we come to this keyway, okay, so nothing over here. No stresses, isn't it? Almost same color, blue and green. Why? Because it's bonded. So it's like a same material. You can say it's the same material. It's bonded, it's glued. Okay, so that's why you do not have any stress over here. Now let's do something different. I do not want this thing. This is global interaction is what? Bonded. I do not want this added definition. Rather, I want that it has a contact. Now, this is important, and we want to discuss this thing before we go further. There are three options over here: bonded, contact, free. Okay, let's discuss these three things. Free means when a part or a face is free, it means there is no constant or interaction applied to it. This means it's going to rotate, even it's going to penetrate inside the material. Okay, it will penetrate inside the material. It's going to consider that there is no material. So the key is going to go inside the keyway, is going to pass all the way through the keyway, and is going to completely rotate 360 degrees. It can move, rotate, and deform without restriction except applied to loads to the boundary condition. If you apply load and boundary condition, then it's going to stop. Otherwise, it's not going to stop because of material interaction. This is important. Okay. If a part is free in an assembly, it will not interact with other component until a contact condition is applied. Okay. So if you apply contact condition, this one, the second one, then it's going to stop. Otherwise, never going to stop. This can be useful in analyzing objects in isolation. What about contact? When a contact is defined between two faces, SolidWorks simulation ensure that these two faces interact according to the specified contact type. So whatever contact type you have, like I have got a keyway, and if there is a restriction, is going to, contact conditions can prevent penetration. This is important. So no penetration is allowed, but in this one, penetration is allowed. Or even sliding. Allow separation. You can separate. Separation is allowed. Sliding is allowed, but penetration is not allowed. This is a very important point. You need to understand this thing. Okay. So is there any problem with this one? Penetration is not allowed. This means one material cannot go inside another material, but they can separate. They can come out. They can come off, and they can slide as well. They can slide onto the surface. Okay. So no penetration. Surface can touch and slide, but cannot pass through each other. Bonded means the surface are stuck together and behave as a single body. So right now, we did an analysis for bonded. Okay. Then what we have, allow penetration means allow surfaces to overlap without resistance. So this free means allow penetration. Okay. And there is something which is called shrink fit. Shrink fit is something when you can say the shaft has a bigger diameter and hole has a smaller diameter. So what happens? You press fit it. That is called shrink fit. So the hole becomes enlarged and the shaft contracts. Okay. So there is also an option for shrink fit as well, which we are going to discuss. But right now we want to have a contact. So this means contact is something which is like a real world thing. Okay. When you have two bodies joined together like this with a keyway and key seat, the best option is contact. And remember, in SolidWorks or any in simulation, you need to understand what is actually the physical world. You need to think and understand about the physical world. If you use this one bonded and do the analysis and say that, okay, my analysis is done, actually you have made a mistake, a big mistake. So you need to understand how the physical world is actually working. Okay, how the parts are interacting together. So I click OK. Okay, so what it says, interaction gap options are changed. Please remesh. Now I have to remesh it. Okay. So, okay, I'm going to remesh because it's yellow now. Yellow means there is some problem. I'm going to remesh it. Okay, so create mesh, click OK. What type? Blended curvature mesh. I'm using the best one. Okay, now result. Run this study. Look, it's taking more time now. Look at the time now. It's not quick. 7 seconds, 8 seconds. This is the time elapsed. Okay. Now the study is done. How to, like come off from here. Okay. So stress plot. One measures the stress. Okay. So this is the stress. Now look at the difference. Where is the maximum? Let's see maximum. Okay, so maximum is over here, here. Where is it? What do you think? Does it make sense? Before the maximum was here. Before the maximum was here. Now it has shifted to this position. What? This corner. Can you see? And it makes sense. Because as you apply force in this direction, this key is going to have, the edge of the key is going to have maximum stress. Okay? This makes sense. But before, it was not red. It was blue. Okay, so we can come to this side. We can show this one and move this one up. Where is the arrow? Okay, so ISO clipping. Section clipping, okay? So move this one up and see what happens at the key side. Okay, so as I move down, look, there are this is the maximum stress. Can you see? This is key and this is key seat, and the maximum stress is something over here on this side. Why it's coming out? Because it's going to come out little bit, but before the deformation is 2.75 times. Maybe it came out little bit, very small amount, but because we have such a large deformation, that's why it's, it's showing you like this. So what you can do, go to edit deformation, okay, make it true scale. So it will go back inside, okay? So you will see that this one, section clipping, so you will see that the maximum stress is actually at the key side, okay? So you need to define this, or you need to design this very carefully. So over here, you are going to have maximum stress. Okay. And one last thing, okay, then we finish. For example, now I know that this area is, is very critical. This area is very critical, and we need to, we need to, analyze this more carefully. So what we are going to do in this situation, we can go over here to mesh, okay? This is show mesh, and there is an option over here, apply mesh control, and this is what I told you that we will discuss at the end, okay? So you can apply mesh control. The mesh control means at some position you want good mesh, and at other position you do not want very fine mesh. At critical regions, for example, you want a very fine mesh, and at non-critical regions you can have a coarse mesh, so to save computation. So what we can do, for example, we know that this is, this curve is something which is critical. Why? Because I haven't made a round over here. And secondly, what I know is that this side, which is actually the other side, okay? So this face, this paddle, this face, you can select all of them. Okay. So other side, you can select this. I have selected the face of the wheel, face of the paddle, edge of the paddle, face of the wheel, and face of the paddle. And let's come to this side. The key side, actually select face boss extrude paddle. Okay. Okay, what should I do now? How to select it? Shall I make it transparent? This is a better way, I think. Change the transparency. Okay. Okay, how to change transparency? Hide, change transparency, isn't it? Is it going to work?
Maybe
Change.
try hiding the object.
Hiding the object.
Yes.
Hide
With the eye
component.
crossed, yes. Yes.
Okay, it's not working, at all. Okay, it's not working. Okay, there is something which is actually not related to explode. Let's explode this. But somehow I can select this one, from here. Create mesh quality, apply mesh control. Oh, there it is. Maybe I have exploded it. So this region, this region, this region, and this region. I want to apply mesh control on these region. And what type of mesh? A fine mesh. Okay. So I want to do the remeshing. Okay. So there it is. Now I can collapse and run this study. Look at this. Now I have got fine mesh, isn't it? But I don't know where the wheel is gone. I think it's hidden, isn't it?
Yes. Yes, because we hide it.
Yeah.
You can unhide it from the tree.
From the tree, yes. To the model tree or from here? I think from here I should unhide it. This is wheel. It's still working. Okay. Okay. So stress to show. And let's go to the wheel and where to unhide it from? Wheel, unhide. Unhide. There is no option for unhide. But anyway, it has given me, the value. But if I click over here, let's go to the model and see if I can do something to unhide it. This is wheel, isn't it? Show component. Yeah, there it is. Okay, so show. So what we got actually, now we see the mesh. So click on this mesh and show the mesh. Look at this. Over here, we have got a fine mesh, and over here, we have got coarse mesh. But you can have fine mesh on that other side as well, okay? But on this side, because I selected the whole surface, I got a finer mesh, and finer mesh means better result, better accuracy, okay? So you can have this finer mesh, and then you can show the result, okay? And then you will see some other value of 1 minus. Look, the red is gone actually. It's somewhere now on the inside, okay? So it was over here before, now it's gone over here. And the values is also changed. We did not, notice it, but definitely the value is going to be a little bit different from before, okay? So this is how you analyze this. Now, what is this? This is actually contact. So when you have contact, this means, look at this side. This side has no interaction, okay? And one more thing, which is the last thing, and then we finish. You can also, in the added definition, you can also define the friction, okay? Maybe you have some friction on this side. So define some reasonable coefficient of friction between the aluminum and the steel and enter it over here. So you can define it. Free means there is going to be no contact, it's going to continuously rotate and gone. Okay. So do not use free over here. Free is used, I don't know for which purposes, but either you are going to use bonded or contact. Normally you will use contact. Okay. So this ends our session, and I hope you learned from it. Is it recorded?